So I will dive straight into the talk. And today an increasing number of devices are based on the ARM-A architecture, most dominantly our smartphones. And if you take a look at the software stack on those devices, you might find an operating system like Android that is based on Linux. And furthermore, the end users are able to install a variety of apps that all have to handle sensitive data. And as a result, the software stack becomes increasingly more complex, which leads to the emergence of bugs. As a response, vendors started to provide a so-called trusted execution environment on those devices, or short TE. And the main idea here is that the TE is completely run isolated from the rest of the system, and that the software stack inside the TE is kept minimal, so no bugs can or should arise inside the TE. And in summary, the TE is designed to be a safe haven for security-critical data like keys or passwords. From a technical perspective, ARM TrustZone is the hardware foundation for providing a TE on those ARM devices. And ARM TrustZone splits the execution into two so-called worlds. On the one side, we have the normal world representing the rich execution environment, and on the other side, the secure world hosting the TE. And any communication between those two worlds has to happen via the so-called secure monitor that is running at the highest privilege level on those devices, and that has access to the entire device, including the TE. And if the normal world wants, for example, request a service from the TE, it has to issue a so-called secure monitor call, or short SMC, and then the monitor can interpret data that is inside shared memory to forward the request to the TrustZone OS or trusted applications. In general, the security of guarantees of ARM TrustZone heavily depend on the quality of firmware that is executed inside the secure world. And as a consequence, recent work looked at those components, especially the TrustZone OS and trusted applications, and successfully found various bugs via fuzzing. However, we started wondering, well, is switching between those worlds really everything this kind of obscure secure monitor does? And especially as it is running at the highest privilege level, and a lot of recent work simply assumed it is bug-free. And so for us, from our perspective, the attack surface to the secure monitor seemed to be rather unexplored. So in our scenario, we assume an attacker that fully compromised the normal world. This is in line with the traditional attacker model from TrustZone, and that the attacker can send arbitrary SMCs to the secure monitor. And this SMC interface is exactly where we then focused our efforts to enable fuzzing of those secure monitors. And we use fuzzing here since this firmware is still written in memory unsafe languages like C that favor the emergence of especially memory corruption bugs. However, applying fuzzing to TrustZone firmware is still a rather difficult task. And one major factor for that is the strongly limited introspection into the firmware that is running inside TrustZone. For example, if we look at a modern smartphone, we will see there are no debug interfaces, and the TE firmware is typically shipped entirely closed source as a proprietary binary by the vendor. So on-device fuzzing is not really a viable option. Instead, we took another route, and we used an approach called rehosting. And the main idea here is that we execute the targeted firmware component, in our case the secure monitor, inside a specifically crafted emulated environment that mimics the original device's hardware. And to accomplish this, we identified two sub-challenges. First, we need a strategy to handle the software dependencies of the secure monitor at runtime. These are mostly from the rich OS, trusted OS, and bootloader components. And second, we need a technique that allows us to handle hardware interactions at runtime, and especially maybe a technique that does not need too much prior knowledge, because hardware on those devices is often also proprietary. A second major challenge when fuzzing secure monitors is the rather complex input space of the SMC interface. So while at first glance the secure monitor simply switches between the normal and the secure world, we found that it has a lot of more tasks. So, for example, vendors can implement several tens of so-called runtime services that can offer a diversity of functionalities. So when an SMC arrives, it is handled by a global dispatcher, and then it is forwarded based on the function ID to a specific runtime service. And each of these runtime services has a unique API, and so a fuzzer without any prior knowledge has a hard time finding good inputs for these runtime services. And here you can see a summarized overview of our approach, which we called EL3XIR. At its core, EL3XIR uses fuzzing to automatically find bugs in a snapshot of a booted secure monitor that we run in an emulated environment. And for guiding you through our fuzzing pipeline, we marked the most interesting components here with numbers 1 to 3. If you take a look at number 1, you can see that we run a snapshot of the booted secure monitor, which allows us fast resets during fuzzing. Marked with 2, you can see our technique called reflected peripheral modeling, where we can automatically solve the hardware dependencies that arise via MMIO of the secure monitor at runtime, and we use fuzzing input to do that. And at number 2, you can see that we synthesize a refined fuzzing harness that effectively knows how to inject input into this complex SMC interface. And in the following, I want to go a little bit more into detail for all of those 3 components. So for our first contribution, we implemented a framework that enables us for partial rehosting of secure monitor binaries. And our rehosting framework is designed to be used by an analyst in an iterative refinement process. And it first starts with an emulator that at least supports the CPU architecture and some fundamental memory layout. And then the analyst can handle step-by-step the arising dependencies. For example, for the software dependencies, the analyst might have to implement smaller software steps for the rich OS, trusted OS, and the bootloader. And for the hardware dependencies at boot time, we might have to implement smaller hardware interactions on the MIO level. And the main idea is here that in the end, we have a snapshot. We have the secure monitor booted up in our emulated environment. We can take a snapshot, and then we can use that for fuzzing. For our second contribution, we tackled the challenge for hardware dependencies during fuzzing, and our approach, which we called reflected peripheral modeling, saves the manual effort of building or implementing manually peripheral models. And instead, we let a fuzzer take on this task on the fly. So after fuzzing, our fuzzing input is initially used to fill the SMC request that is sent via the SMC interface. We use the remaining bytes as inputs via the MIO interface as MIO actions for the emulator. And for injecting these hardware interactions, we implemented a mechanism that allows us to hook the execution of the secure monitor at runtime exactly when an MIO read event happens. And the underlying idea here is that at some point, our fuzzer will find a good input that allows the secure monitor to overcome coverage walls that would arise due to missing peripherals. For our third contribution, we tackled the challenge of handling the complex input space for the SMC interface. And for our approach, we synthesize a refined fuzzing harness that is based on the source code of the rich execution environments OS. And the idea is that the rich OS has drivers that communicate with the TE. So we want to derive this knowledge from these drivers and recover prototypical function interfaces that then match those of the runtime services found in the secure monitor. And for that, we start by compiling the rich OS source code or a partition of it with LLVM, and then we perform a static analysis starting at SMC call sites backwards, and then we can derive interface candidates that look like those of runtime services. And in a third phase, after we have those interface candidates, we additionally use a probing phase where we test these interface candidates together with other function seeds and compare the reached coverage profile. And this allows us to prune false positive and additionally find new runtime services that our rich OS did not use before. For our evaluation, we tested EL3XIR against 7 targets of 6 vendors. 4 were open source and 3 closed source. And overall, we found 17 security-relevant bugs with EL3XIR. Compared to a naive fuzzing baseline, we found more bugs. And in summary, we got 6 CVEs assigned out of those 17 bugs by the affected vendors. And furthermore, we also evaluated EL3XIR in terms of reachable edge code coverage and compared it to a naive fuzzing baseline. Since there is no real fuzzing baseline there, because we are the first to target the secure monitors, we run multiple fuzzing experiments where we switched on and off the harness synthesis and the reflected peripheral modeling techniques. And you may have a look at the paper for more details, but in summary, EL3XIR outperformed the naive fuzzer in terms of code coverage for all of our targets. And this shows that we need approaches like EL3XIR to fuzz highly intertwined software or firmware components like secure monitors. So in summary, we present EL3XIR, an end-to-end framework for fuzzing commercial off-the-shelf secure monitor binaries. We presented our 3 main contributions. First of all, a rehosting framework for addressing TrustZone binaries. Second, a reflected peripheral modeling approach that allows us to handle hardware interactions on the fly. And third, our generation of a refined fuzzing harness that knows how to effectively fuzz the SMC interface. So our fuzzing pipeline is highly automated, and we also took part in the artifact evaluation, so you can find our source code openly accessible at GitHub. So with that, have fun and maybe fuzz your own secure monitor, and thanks for your attention.